Hi, my name is Abigail Reynolds, and this is my Lab 5 video report on Faraday's Law. The purpose of this lab was to observe the difference between a magnet falling through a non-ferrous tube and a magnet in free fall. After experimentation and data collection, the system was modeled using code, and actual results were compared to the simulated results. The actual time was 1.65 seconds, and the simulated time was 1.892 seconds. The physics principles involved in this lab include the following. Faraday's law was used to find the current in each small ring of the tube. Biot-Savart law was used to find the magnetic force and field on each current-carrying ring. Newton's second law was used to update the position and velocity of the magnet in code, and Newton's third law was used to find the force exerted by the tube of rings on the falling magnet. The materials needed for the experiment were a roll of aluminum foil, a bar magnet, a smartphone, and a tool to measure tube dimensions. For methods, suspend the roll of aluminum in the air so that the magnet exiting the tube will be visible, then suspend the magnet above the roll. Position the smartphone camera so that the setup is in view. Press record and drop the magnet through the tube. For observations, I originally predicted that the magnet would fall through the tube quickly, but it experienced some resistance and fell much slower than expected. Also, the magnet enters tube down vertically and exits down vertically, which is the same direction. 5 trials were completed and averaged together to find the average time of the data set. This was calculated to be 1.65 seconds. The dimensions of the aluminum roll and mu mag from Lab 3 are shown. The aluminum roll length was measured to be 0.312 meters. The aluminum roll width was measured to be 0.0083 meters, and the inner radius of the tube was measured to be 0.0175 meters. Mu mag from Lab 3 was used as 2.24. The next step of the experiment was to use code to create a simulation of the experiment. In the first part of the code, constants are initialized. The simulation is set up to see the tube of foil as a series of rings, and the aluminum tube and falling magnet are created. Next, the magnet is created at rest using mu mag from Lab 3. Then functions were coded to find the magnetic field and d flux over dt. Next, visuals for output are created. Here shown are the calculations for current in each ring, magnetic field of each ring, and the total magnetic force acting on the magnet. This last piece of code updates the net force, velocity, and position of the magnet inside the while loop. This loop is set to run until the magnet has completely exited the tube. The graph on the upper right shows velocity versus time. Here, the black cylinder represents the tube of foil, the red area represents the increasing current below the magnet, and the blue area represents the decreasing current above the magnet. The magnet takes 1.892 seconds to fall through the tube in the simulation. In conclusion, we can determine that free fall would be much faster than dropping the magnet in the tube. This is because there would be no major magnetic force resisting the fall. From comparing the result from the actual experiment to the simulation, percent error was calculated to be 12.8%. This could be due to error in this lab's experimentation or error from calculating the magnetic dipole moment of the magnet in Lab 3. What if the resistivity of the conductor was reduced as close as possible to zero? How would the dynamics of the falling magnet change? If the resistivity of the conductor was reduced, this would increase the induced current and the magnet would fall slower. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? If holes or slots were cut into the tube, this would reduce the number of complete rings making up the tube. Induced current would decrease and the magnet would fall faster.